So it's a real pleasure to have with us today Professor Hong Yo, who's relatively new to Georgia Tech, so it's a good chance for us to get to know him. Hong did his undergraduate work in mechanical engineering in South Korea before going to the University of Washington, where he got his PhD in mechanical engineering and genome sciences, and then did a postdoc at the University of Illinois, Urbana-Champaign, before spending a couple of years at Virginia Commonwealth University as an assistant professor, and then coming to Georgia Tech just last year, where he's currently an assistant professor in mechanical engineering and the bioengineering program. He's won a number of awards and sits on editorial boards of journals as well. And his research is in the kind of the broad areas of engineering and biology interface. And so I'll let him tell us about that today.
Right. Thanks for nice introduction. Thanks for having me here. It's my great pleasure to introduce some of my research works regarding soft electronics. Our research group is housed in this building, actually. We are having a few undergrad students, graduate students, and postdocs. We are working on soft materials and soft functional materials, including both organic and inorganic, to design biosensors and bioelectronics. So we design these biosystems. Yes?
Can you use the microphone? We can't hear you that good.
So there's no microphone for this room.
I do have here,
the
but
microphone is for the camera only.
I'll speak loudly. Okay. Right. But can you hear me now? Better? Okay. So let me go back. Start over. All right. So we are studying soft and functional materials to design biosensors and bioelectronics. I'm mostly targeting for applications in wearable and implantable devices. So in general, we are working with these bio-integrated devices and systems for advancing healthcare and persistent human-machine interfaces. As you may know, there are many different types of biomedical devices, including wearable devices in these days, and implantable systems, endoscopes, nuclear neurostimulator, cochlear implant, drug delivery systems, and so on. Among those, as I said, our main focus of research is to study materials to design systems for wearable, implantable applications. When I started this research, I found an interesting issue. So as you can imagine, we are developing these biomedical devices by targeting human, right? So we are trying to wear this device or include this device into the body for health monitoring, disease diagnostics, or even therapeutics. So if you look at our human tissues, external tissues like our skin, internal tissues including organs, these are made of soft materials. In terms of Young's modulus in mechanical engineering term, they are in about kilopascals range. So they are soft, they are deformable, stretchable, and if you look at the surface, like skin or organs, they have curvilinear and contoured geometries. And what about the existing medical devices? So here I put some examples, including hydration monitor, implantable devices, neurostimulator, surface-mounted electrode for recording biopotentials from the body. They are miniaturized these days. People keep trying to miniaturize further and further, but still they are bulky. And the problem is the materials that they use normally are metals and plastics. So they have flat and rigid properties. So if you compare these existing devices with targeted tissues and organs, you can easily see that there's fundamental mismatch in terms of mechanics and materials. So this mismatch causes issues of conformal intimate lamination for high quality signal recording or for effective therapeutics. Let me give you a specific example here. There is biomedical monitor called electrocardiogram monitor, which can be skin mounted. So it's measuring biopotentials. So here's a baby. His parent knew that he has some abnormal issues with heart, so he brought into this hospital. So what doctors do at the very beginning is they look at how heart functions by using this electrode, surface-mounted electrode, normally made of either gold, tin, or silver. What do you see from this picture? So baby is tiny, and as you can imagine, baby's skin is very soft and fragile. But he has to wear this electrode, which is rigid and hard. And it's very obtrusive and intimidating, right? It looks scary if you look at these many wires and these clips. And to put this electrode onto the skin for monitoring electrocardiograms, they have to use these blue tapes, which can damage their tissues once they put multiple tapes over the skin. Obviously, they use a lot of wires and separate powering and the data telemetry system for signal recording. So overall, it's not nice for sure, but it's not ideal for small babies, even others, because of the size and the material that they used. So people are working on miniaturization of these devices by having this type of portable monitor with smaller number of wires, or even most recently, a big biomedical company in the United States, Medtronic, released a new biomedical system for measuring electrocardiogram called SICK. So this one single device can do pretty much everything that this device does. Looks a lot nice, right? Now this device has electrode and electronic circuit to filter the signal and process those signals, and then finally send the signal to your smartphone or tablet via Bluetooth. Right? Looks a lot better. But if you look at the device closely, they still use the same material, even though they miniaturize everything. They use metals and plastics. They use gold to make the electrode to be mounted on the skin. Obviously, it's based on metal and the plastics to encapsulate everything, so it's heavy. Right? So they have to use a sticky tape to put them onto the skin. It could be okay for wearing this device for, I guess, 1 or 2 hours, but nobody wants to wear this more than a day or a week because it's heavy. I tried it. Believe me, it's not comfortable, right? And it's very obtrusive. So if you imagine that somebody has to wear this device for continuous health monitoring during daily activities or during working, it's not ideal. So we have to change this material because they still use the same materials. We have a bigger issue once you look at the interface between the device and the skin. Again, this device is mounted on the skin for monitoring electrocardiograms. If you look at your skin, it looks flat, but if you look at closely in terms of microscopic view, you have this wavy pattern. So normally we have about hundreds to 500 micrometers in terms of wavelengths and amplitude difference onto the skin surface. So as you can imagine, the metal, gold, tin, or silver, they are rigid and flat. So if you put that electrode onto your skin, then you will see an air gap between those two materials, which is bad for signal recording because it can enhance electrical impedance. So people found out that we can use a liquid gel made of sodium chloride, right? So here they put this gel. Then now, as you can see, there's no air gap because this gel can cover those space. So now you are ready to record nice biopotential, right? So problem solved. That's good. Problem solved for a short-term period. So sadly, if you wear this device for long term, like more than 5 hours, more than a day, you can see this problem. It's my skin, and I put this electrode on my skin, again with the gel and metal, and I use this tape to put on my skin. After 5 hours, I detach it, and I use this infrared camera to see the temperature variation over my skin. What do you see? So that's the location where I put this electrode with the gel. Now you see this elevated temperature. Right? They can cause skin irritation, skin redness, and allergic reactions. Right? So that's bad. Nobody wants to wear this by irritating your skin for a long time. But on the other hand, the bigger issue is here. Now, in terms of signal quality, that's what you want. You want to have nice high fidelity electrical signal of electrocardiogram. But now, since this electrolyte gel is evaporating over time, right? So now you have this gap. Then the problem is your electrical impedance is increasing, so your baseline noise is also increasing, so you're losing the quality of your electrocardiogram signal. So that's really bad in terms of signal recording. And now we have to address those issues, right? We need to remove those gel. We need to make it lighter and more wearable. So we came up with this idea to make the electronics like our skin. So we call it as skin-like electronics. Why? Because now this type of electronics is looking like our skin by following the mechanical and material properties of the targeted tissue, which is our skin. Now you see that this surface-mounted electrode is ultralight, less than 1 gram, and ultra-thin, less than 1 micrometer. And as you see that, it's not obtrusive at all, right? And if you take a look at closely, I'm going to talk about that later, it's made of mesh structures. Right? So you can follow the time dynamic motions of your skin deformation without fracturing the device. Right? So it's going to be a lot more comfortable, and it's designed in a way that it can be wearable for a long time, not a couple of hours. Right. Then you may ask me, how can you design such a thing? Right? So we have to look at flexibility first. We can get this flexibility of materials from this simple equation from mechanics, EI. The E stands for the Young's modulus, and I is for second moment of inertia. So this bending stiffness, EI, is proportional to the thickness cube of the material. So, for example, we have silicon, right? I assume somebody is working on electrical engineering knows silicon. We use silicon for making semiconductor circuits and everything. As you know, silicon is rigid and brittle. Right? If you drop that silicon wafer, like 500 micron thick wafer, we drop it here to the bottom, it's going to be fractured right away. And in terms of modulus, this guy has 10 gigapascals, right? Pretty rigid. Can you bend it? Can you make it flexed? It's not possible. But with the same material, you can make it flexible by reducing thickness, right? Same silicon now is bendable. Why? Because you reduced the bending stiffness by thinning your material. So like this silicon, you can make gold, silver, or tin, copper flexible by just reducing the thickness. Right? So that's the key to make this flexible electronics with these core materials that we normally use for electronics. At the same time, once you reduce the thickness, you can get another advantage, which is about this crack propagation. If you put two materials together, then there's crack propagation happens from the energy relation. But if you reduce the thickness, then you can get that benefit as well by reducing this energy release rate. Now, this device is made of silicon nanomembrane on this photoresist pattern. So it's cantilever. We didn't use any adhesive. It's purely based on van-der-Waals interaction between two materials. But without that adhesive, you have negligible crack propagation in terms of energy. So now we can have this structure. So in the same way, you can build multiple patterns or even more complicated 3D structures based on this nanomembrane. So that's the beauty of thin material. Okay, now let's revisit this illustration that I showed you earlier. So we have this rigid flat electrode. That's why we have to use this problematic gel, right? Now, if you remove this gel by using ultra thin electrode, such that it can follow the morphology of your skin, then you can have this dry configuration, right? So we don't need to worry about gel evaporation, skin irritation anymore. Okay, so problem solved by using ultra thin membrane. Then somebody asked me how thin it needs to be, right? Should it make it like nano thick, nanoscale thick, or microscale thick? That's a good question because it's really hard to make it nanomembrane. So we calculated the ideal device thickness to have this flexibility, specifically here to have intimate and conformal lamination over the skin surface. So we did a simple analytical calculation based on this skin morphology in a sinusoidal form. And we consider this case where your electrode is having this nice conformal contact to the skin. At that interface, what you can do is we can calculate this interfacial energy related to the bending energy of your electrode and skin elastic energy and adhesion energy. Right? So here in this equation, bending and elastic energy are negative and adhesion energy is positive. So this conformal contact can be determined when the adhesion energy is bigger than the sum of those bending and skin elastic energy. So by solving this equation, we got this governing equation having this skin modulus, amplitude, wavelengths, and so on, along with this EI term again, as I showed you earlier, bending stiffness, right? So this term is related to the thickness of your material. Then by solving this equation, you got this nice plot showing the relationship between interface energy and the membrane thickness. So as you can see, we start from 100 micrometers, right? We reduce the thickness from 100 to 1 micrometers. Now you see that the value was negative, but after 20-something micrometers, it becomes positive. So now your bending and skin elastic energy becomes negligible so that you can get this nice conformal contact. So based on average values of your skin parameters, it's not applicable for everybody, but we use average values of skin parameters to calculate this critical thickness of membrane for having conformal contact, which was about 25 micrometers. So if you reduce whatever material you have under this thickness, then it becomes flexible, and then it can start follow the morphology of your skin.
Is that just for silicon or for any material?
A good question. We tested silicon and metal, gold. Okay, so to prove this, we did a simple experiment to visualize how the lamination of electrode onto the skin looking like. So that's scanning electron microscope image, and here this black background is my skin, right? As I told you, that skin is not flat, right? It has these nice wavy patterns, okay? And I put this electrode membrane having the thickness 100 micrometers. And now, as you can see that there is an air gap, right? So we have to reduce the thickness further. So now about 35 micrometers, you see that looks a lot better compared to this guy, but still we have gaps. So I reduce further and further. So now 5 micrometer thick membrane. As you see that it has pretty nice conformal contact to the skin surface. If you zoom in, then now you see this nice gold electrode is following the background, which is the skin. Okay? So by using this ultra thin electrode, you don't need to use this conductive gel so that you have completely dry configuration for measuring biopotentials, like electrocardiogram that I mentioned earlier. All right? And that's actually my skin with microscope, right? So even though it looks dark here, but based on microscope, it is very clean and white. And as you see that my skin has these wavy patterns, right? And that's printed electrode over the skin. So it looks very good in terms of this contact. We can also do quantitative measurement, right, in terms of electrical signal. So we could measure this contact impedance between skin and electrode. And based on this equation, the contact impedance is inversely proportional to the contact area. Here, A, right? Then if contact area increases, your overall impedance decreases. Right? So when you compare two different cases where you have nice contact of your electrode versus poor contact of your electrode, nice contact of your electrode can give you better or large contact area, right? So that's something we want to measure it here. So we put this electrode onto the skin and measure these impedance values. And as you see here, we started from 500 micrometers, and we reduced the thickness further and further down to 5 micrometers. And as you can see that with 5 micrometer, we have pretty low electrical impedance, about 20 kilo ohms compared to the thick membrane. So with this value, 20 kilo ohms, even without the gel, we can get nice quality of biopotentials from the skin. All right, that's how we can utilize the flexibility of material to design electrode. And what about stretchability? Right? Our external tissue like skin or internal organs, they are all moving. They have time dynamic deformation, right? They have cyclic loading, stress, strain. So the device should be stretchable as well by considering also their 3D geometry. You can simply utilize a new pattern when you design your electrode or system. So instead of using linear straight lines to design electrode or electronics, we came up with these open mesh serpentine-like structures. Right? So basically we give rooms to be stretched, while it's also flexible based on the thickness. So based on this finite element modeling, you can imagine how much stress can be applied and whether this material is fractured or not. So here in this case, we have this gold membrane, 200 nanometer in terms of thickness. And with 30% strain, it's not going to be fractured and stretchable as shown over here. Right? Why 30%? It's based on our targeted skin. Our skin has maximum stretchability of 30%. After that, it's going to be having tissue damage. But if you look at like elbow or joints and other areas, it can be even higher than 30%. So if you look at those areas, then you can modify your design. So instead of that, now we call it island bridge. So you have these islands, and there's a bridge interconnects based on these serpentine structures. Now this guy can be stretched up to 100% or even higher. So depending on your applications or targeted locations, you can tailor your design so that you can have maximum stretchability without fracturing your electrode or electronics. Right. You may ask me, how can we fabricate such things? Okay? So overall, we are following the conventional microfabrication techniques. So I know that some of you here are working on this microfabrication. So we use this microfabrication facility to design and pattern the targeted electrode and electronic components on a silicon wafer. But we have a little trick here. Instead of having the conventional processes, right on this silicon wafer, we had a polymer membrane, ultra thin, about 200 nanometer thick polymer, PMMA. We coat it before metallization or for lithography. And then after finishing pattern, we release that, we dissolve that polymer membrane. Then we can dissociate these electronics from the silicon wafer by using a sticky elastomeric stamp or like water-soluble tape or anything that you like. Something is sticky, right? Then you can dissociate this guy, which was floating from the carrying silicon wafer. And now you can play with this electronics for many different things. Now you can put this guy onto your skin or onto like flexible membrane, stretchable membrane, medical bandage, anything like that. But here, as an example, we can put this electrode, gold electrode, onto the skin directly by using a sprayed glue layer. And then after transferring this guy, you can encapsulate with waterproof polymer, thin coating about 1 to 2 micrometers. Then you can wear this electrode for more than 2 weeks, up to a month or more, depending on how you encapsulate it. Right? So for better understanding here, I prepared a video clip. That's a service. Okay, so that's one of methodologies that you can print your thin electrode onto the skin. All right, now what's next? So we have this ultra thin, flexible, and stretchable electrode. What you can do? We can obviously do the electrocardiogram monitoring, something that I showed you earlier. But here I want to talk about today for 2 different examples. First one is about human-machine interfaces. People talked about this for a few years already. So we are working on a few different projects, but here I want to start with this wireless wheelchair interface. As you may know that a lot of people in the United States are relying on this wheelchair, more than 3 million people. Sadly, among them, about 10% have motor disability. So like people with Parkinson's, they have this hand tremor. Okay, so as you can see that this gentleman is having hard time to eat or to do some regular activities because of these hand tremors. And now you need to imagine that you have to use this hand to control an electronic wheelchair based on joysticks. Right? It's going to be really hard to control or nice control your electronic wheelchair with this motor disability. Okay, so that's the motivation of this work. So how about having new type of wheelchair interface to remove this hand control? So we need to find an alternative way, right? There are many different ways to make a new interface, but we approach it from looking at biopotentials. Okay? One of them I already told you, electrocardiogram from our heart. There are many different biopotentials, including the brain signal. It's coming from your scalp. When you think, when you look, when you do something with your brain, we can measure that electric potential onto the surface of your scalp, which is called electroencephalograms, EEG. We are working on the project, but here I'm not going to talk about the project today. I want to talk about this muscle activity based on biopotentials. One of them is electroocculograms. Okay? So if you look at your eye, then the eye is going to be moving based on your muscles, right? Okay? So we can measure these biopotentials by using the surface-mounted electrode onto the skin. Completely non-invasive, right? You're not poking anything onto your tissue. So the idea is to utilize these electroocculograms to control the wheelchair. Okay? So start with this simple biology. So that's an illustration of our eye, right? So corneal side is positively polarized. So it's polarized, and cornea is positively charged, and retina is negatively charged. So when the eyeball moves, then electric potential generates. So when you use a pair of electrode, right, putting on your skin, whether horizontal direction or vertical direction, when your eyeball is moving from neutral location to either horizontally or vertically, then now you can measure the biopotential by using this pair of electrode. Okay? So this positive side, when this eyeball is moving to this direction, then now you have this nice biopotential, normally about hundreds of microvolts, which is really high. Microvolts, compared to other signals like from the brain. The EEG, electroencephalogram that I mentioned earlier, you get normally tens of microvolts. But now from these muscle activities, you get hundreds of microvolts. So compared to your typical background noise from your body, which is about 10 microvolts or smaller than that, you can easily distinguish this signal. So if you move your eyeball to the negative side, then now you have this negative biopotential. Obviously, based on the degree of your eyeball movement, you can get different biopotential. Okay, so by utilizing these electroaccurograms, we design a new system. Okay, now we have wheelchair, exactly the same as before, electronic wheelchair, but there's no joystick, right? This guy has hand problem, so he cannot use joystick. No joystick, electronic wheelchair, but now you see different things around his eyes. Now he has this skin-mounted electrode, right? Ultra-thin electrode that can be stretchable up to 100%. But if you take a close look, then now you have this nice conformal contact without the gel, right? So membrane-based electrode, unobtrusive, and it can measure the eye movement in two different directions, horizontally or vertically. And we record that electropotential, and it's going to be communicating with this data acquisition system on a tablet, and now it's connected to the wheelchair to control it. Right? And how can you measure this electroacourogram by using soft electrode? So we have this electrode here, there, one pair for monitoring vertical motion. A second pair to measure the horizontal motion here and there, or one can be on the nose. And you have the fifth one onto the forehead to measure the common ground so that you can eject that common ground noise from the signal. So now you see this guy is moving eye up, down. You have this about 400 microvolts of biopotential. And you can filter them to have this nice peak based on threshold. At the same time, you can do horizontal motion recording, right? Left and right. Okay? And here we have two different curves. The blue one is the mesh pattern fractal soft electrode, and the red one is conventional gel-based metal electrode. We have simultaneous comparison. Looks pretty similar. Right? Then we had this performance comparison to see whether our electrode, the soft electrode, is as good as the conventional gel-based electrode. So this person is wearing two types of electrode at the same time, and I asked her to move the eye from 0 to up to 40 degrees. And we measured the electroaccurograms. As you see that as eye moves further and further, you have this increase of biopotential. So about 11.7 microvolts per degree for conventional, and about 13 microvolts per degree for soft electrode. So interestingly, even our soft electrode has higher signal compared to gel-based electrode. It's very interesting, right? So we check why. And we found out that, when you look at this electrode over here, we design our electrode by following the size of the conventional, which is about 1 centimeter square, right? But the thing is, if you look at this conventional thing, they are using the metal and the gel. Again, the metal and the wire are heavy. So they have to use this tape, right? They have to use some of this area to put this guy onto the skin. But instead of that, our electrode is completely soft and conformably laminated onto the skin. So we don't need to use that overall adhesion areas. So compared to that, we are getting we are getting bigger surface area compared to the gel electrode. So the quarter fractal, quarter size of the electrode is similar to the conventional electrode, which is good. We are getting higher signal to noise ratio with comfortable lamination. Then now we can classify this signal for controlling the wheelchair. So we have this raw signal, and now we can filter them. And we are using different features in MATLAB to classify this. All right, based on threshold, now we have this threshold map based on LDA linear discrete analysis classifier. All right, we have up, down, left, right, 4 motions, 4 eye motions. And based on this combination of features, we can have nice classification. So based on our test with 3 subjects, we got average accuracy of 94% overall. So if you see this confusion matrix, which is showing the predicted class from the calculation or actual class from the actual test, you see that up-down motion are perfect, but we have some confusion between left and right. But overall, we have 94, which is even higher than the conventional gel, 92%. As I mentioned, that we have higher signal-to-noise ratio with better area coverage. Okay? So now we are ready to control something. Here, wheelchair. So that's an electronic wheelchair, and we put this tablet with customized graphic user interface. So this first channel window is looking at the vertical motion, and the second channel window is looking at horizontal motion. And we have this classified the signal command to control the wheelchair moving forward, turning left and right, or stop. Okay? So instead of this joystick, we put this Bluetooth module and microcontroller so that this wheelchair can communicate through this interface based on wireless electronics. Right. Now we have this nice subject who's wearing the 2 pairs of electrode, right? And I asked him to follow this track over here. Right? So actually that's what it is. So on the floor we mark this track, and this guy will control the wheelchair, right? Based on eye movement, not a joystick. So go forward, and here turning clockwise, no, counterclockwise, and forward, clockwise rotation, and finally stop over there. So here this movie is showing his eye movement, which is really quick. I don't know whether you can see that, but you can see the signal change from this data acquisition system. So eye up, start to move. Eye left, counterclockwise rotation. That's Ferrari engine sound, not from wheelchair. Well, sounds good, so that's why I put it in. Right? Ferrari wheelchair. All right, so that's how we can utilize the 4 classes to control this wheelchair. All right, that's a simple example of utilizing biopotential with surface-mounted skin-like electrode. The next thing that I want to talk about is about exoskeleton prosthesis. It's one of the projects that we are working on. So the goal is to make this exoskeleton prosthesis and glove, exoskeleton glove, controlled via biopotentials. Like this, that's a robotic arm, as a glove to enhance the gripping force, to help people who have injured on their hands or wrist, or to help patients for their rehabilitation based on this glove, or to help somebody who have amputation. Okay? So instead of having just regular prosthetic device, this guy is electronic prosthetic device that can be controlled via biopotential. So the idea is pretty similar. We are trying to utilize our muscle activities, or here muscle activities, which is called electromyograms. So we get the biopotentials from the skin based on skin-mounted electrode. When we do, and then we do the signal filtering, processing, and communicate with the targeted robotic hands or glove to control. So here, to measure the electromyogram, so now electromyogram is coming from your muscle. So here we are targeting our forearm, right? So here we have a lot of muscles, and by mounting this electrode, now this electrode is on a bandage, flexible bandage that we normally use. And as you see, I don't know whether you can see, there is a GT, Georgia Tech electrode that we designed. And then it's going to be mounted over the targeted muscle. So if you move your fingers or your hand, there's a big muscle is activated. It's called electrocapillary radialis. So by putting this electrode over there, you can pick up many different types of biopotentials. Right? So here, when you move your hand in that way, or this way, or squeezing, or move your fingers, you can get different types of signals in terms of frequency and amplitude. And we process those signals to communicate with this guy, here prosthetic arm, with 3D printed components, and we added the rotors and strings to control this guy. And then among these 4 arms, we selected 3 locations from this anatomy. So instead of putting the electrode all over the surface to get the signals from 5 different fingers, we found out that there are merging location of two different muscles, right, here and there. So instead of using an array of electrodes, by using 3 electrodes, we can measure the 5 different finger movement. So we did this mapping of electromyogram signals, and as you see that here, there, and there, we get pretty good electromyogram strength. So we designed this electrode and mounted over there, and to control this guy. So here we have 7 different classes, open, close, and 5 different fingers, right, to control this guy. And in terms of confusion matrix that I showed you earlier here, and now we are getting about 98% of accuracy. So it's going to be controlling like this. There is a little bit of confusion. Not perfect. 98%. Right? So that's how we can utilize the biopotential called electromyograms to control a robotic hand. In a similar way, we can design this exoskeleton hand to enhance the gripping force. For people who have weakness. So by using this linear actuator, this guy can maximize the power 50 newtons, which is small, but you can change the linear actuator to have higher force. And we have 3 printed parts connected with this glove so that it can follow the motions of your finger. So this guy has 7 classes as before. We are recording the electromyogram from the same location, 3 different locations, and this guy is following that motions in that way. 100% accuracy. Right. So that's how we utilize the our electrodes for human-machine interfaces. The last thing that I want to quickly share is about human health monitoring. So it's to design new type of artificial taste system to help people with issues tasting something, right? So we got this idea to utilize dental retainer, right? For elderly people, they tend to use this dental retainer. So how about putting ultra nice thin electrode or electronics onto this retainer? Then it's going to be comfortable for them to wear it in daily activity. So we designed this nice ultra thin circuit, and this guy has Bluetooth powered by this coin cell, so you can communicate with this smartphone or tablet to record what kind of taste that I'm getting from food intake, right? So this device is mounted on the pallet, again on this dental retainer. It's ultra thin, less than 2 millimeters in terms of thickness. So the thickness, the circuit itself is ultra thin, but this circuit, the chip component, right? That guy is about, I believe, 3 millimeters in height. But other than that, it's ultra thin, as you can see from here. So as an example, we designed a sodium electrode to measure the saltiness, right? Or we can help people with hypertension. So we are trying to utilize this device to alert them, okay, stop eating potato chips, you are taking too much sodiums, right? Or pizzas. Sorry for you guys, but pizzas or things like that. So first example, to design this membrane sodium sensor based on the polymer. Now you can see this nice curve based on different sodium concentration. we designed this micro electrode ultra thin so that it can be accommodated with this circuit. And we have selectivity of sodium among other ions, so that we have this nice curve, linear curve based on sodium concentration of the sensor. In a similar way, we can design pH sensor, right? Targeting, sourness, for example. Here we have this nice value of voltage change according to the pH value. One example here, actually this guy is our victim to wear this device to test it, to see whether it's really working. So this guy is putting this device onto his palate, and we ask him to drink a lot of water with different pH to see how that works. And now it's communicating to this tablet via Bluetooth, as I told you. So now this Bluetooth, this tablet is recording the pH values. Hobbit music. This guy is putting that electronics onto the pallet. Start with acidic water, which is pH 4. I don't know whether you can see the number here, but that's 4. Yeah, that's how this device works. All right, so today I briefly introduce what we are working on in terms of soft materials and mechanics and system integration to design smart and connected bioelectronics. And we are doing this research to advance human healthcare and wellness. I'd like to thank the research sponsors, and thank you for your attention. Yes.
What is the stamp that you were using to transfer it? What is the stamp? How do you transfer the metal to the stamp?
What is a stamp?
And also one other question.
Yeah.
What is the elastomer material? Like in all of the slides you had an elastomer. Is that the same all across the different applications that you showed, or is it different for different applications?
Right. Well, the first question, the stamp we utilized PDMS, polydimethylsiloxane, or you can use different materials too. I think it's going to be answering your question number 2 as well. We are using different types of silicone elastomer, not just PDMS, but we don't fabricate or we don't mix our own elastomer. We buy from commercial sources or different brands, and using different elastomers because we are targeting different Young's modulus depending on applications. So it's not the same all the way from the beginning to the end. Depending on the structure and the targeted stiffness, we manipulate that modulus from 1 megapascal down to 1 kilopascal. Okay? And I dissociated the electronics from the silicon wafer by putting the desirable polymer at the very beginning between these two materials. PMMA. Yes?
For the device that was the pallet that the subject had in his mouth, are the components passivated from the outside environment, or are they exposed?
Good question. For that intraoral application, right, to avoid that electric shock or something, we encapsulate everything with polyimide as well as silicone elastomer. So the double coating of those material, except the opening of the contact electrode. Yes?
For the wheelchair and other, how many wires are coming out of it? The recording, this one was wireless, right? But
Yes.
the others, was it wireless as well, or was it wired?
Wheelchair was wired from the electrode to the data telemetry system, but the hand thing was powered by this circuit that I showed you earlier. I don't know whether you saw that there's the electrode, and right next to it, there's this wearable thin circuit as well. That's also flexible because we utilize a nanomembrane to put the electronic components. So some with wire, some with wireless.
So from all those electrodes, so for the one that was the ocular one, how many wires actually transmit?
How many? There are 5 wires because we utilize 5 electrodes, 2 pairs, 1 ground. Okay, 5 wires coming out of electrode, and then it's going to be housed into that Bluetooth telemetry system. Yes.
So given that this is sort of designed for long-term use, like how will you get around the wires or make it a little bit more wearable, practical, and all that?
Good question. So, as I told you, told him, thus far we tested different designs, different versions of electronics, and now we are trying to have one single patch, still ultra thin, with the electronics together. So on top of it, there's going to be electronics for communication and powering, and the bottom of that electronics will include the electrode, so they can be mounted on the skin. So we're trying to have same entire size, but with small form factor, using the same type of flexible nanomembrane. So for
Like power and telemetry and all that?
yeah, the only thing limiting our capability is the power source. The intraoral electronics thing, we utilize a small coin cell, but it's not going to be powering for multiple days. But I think depending on application, we don't need that long-term powering. We can recharge it after like a day or something. So that's the only hurdle to miniaturize everything. But other than that, all other circuit components and circuit interconnects are already miniaturized and ultra thin. So that's the biggest component. But still, we are not using metals or bulky metals and plastics. So it's still ultra light and comfortable to wear. Yes?
I have a simple question. What material of metal is using? Do you use just gold only, or just use add some adhesion layer in between those layers?
Good question. For surface-mounted electrode, right, to record biopotentials, we normally use gold membrane, gold nanomembrane, normally 100 or 200 nanometer thick. For electronics, the circuit design, right, to design this stretchable or flexible interconnects, we use copper. We use deposited copper so that we can mount the chip components for functionality. Yes?
Related to this question, so it has to do with power. So say, I don't know if your long-term plan is to always have some power source always attached to the electronics, or if you wanted to wirelessly power it, but how much of a problem do you think the flexible nature of the electronics will have if you wanted to do, say, inductive power?
Inductive powering?
Yeah, or some wireless form of power.
Good question. That's something I want to work on as well. We are not powering group. We are not studying really this, energy harvesting or things like that. So I'm trying to collaborate with guys who are doing those things. Thus far, we are only using those coin cell and other lithium-ion batteries. But obviously, for long-term or even implantable electronics, we have to remove those batteries, right, which is not good for our body. So I cannot answer your question right now, but that's something I want to answer you later.
One more.
Yes?
Is there any prospect to make it transparent by using nanowires or other materials or another strategy?
Transparent of the entire electronics?
Yeah, so you can stick it on the skin and you don't see it.
We haven't tried, but obviously if you utilize those transparent material, maybe you can do that to make it unobtrusive. Well, we haven't tried it. Thus far, we only utilized pretty much inorganic, gold, metal, and other stuff. These days, we are playing with carbon nanotubes and nanowire to design the electrode portion, not the entire device.
Let's thank Han one more time.
Thank you.